Stan Gibilisco here with a little discussion about inverse function variables and how we name them. There's a little bit of confusion that a reader brought up in my book, Calculus Know-It-All. Please refer to quiz question 3 in chapter 1. You will find that on page 19, and the explanation and answer on page 590. Now basically this is a particular example of an inverse function and how we name the variables of the function itself and its inverse. Keep in mind that functions don't always have inverses that are functions, but in this particular case we have a function that does have an inverse. Let's just take a generic example. We don't even necessarily have to specify any formula whatsoever. Well, that's not going to work. That's not going to work. Because, well, you'll find out why if you try to take the inverse of this particular beast. But let's just consider a linear function or something that, well, just something like that. And we consider that we call this function f of x. Here's the x-axis. The independent variable goes horizontally along the x-axis, and y here is the dependent variable along the vertical axis. So we can say here now that y equals f of x. The value of y at any particular point, that is, say right here, depends on the value of x. It is a function of the value of x, and we know it's a function because if you draw vertical lines and a vertical line and move it back and forth, it'll never intersect this curve at more than one point. That's all discussed in chapter 1 of Calculus Know-It-All, and a good deal also in my book Pre-Calculus Know-It-All. But for right now, let's just keep in mind y equals f of x. Now if we take the inverse of that, what we want to do basically is see whether or not we can consider x as a function of y instead. And we have to do some mathematical manipulations to have that happen. And when we do that, we'll get some other curve on this xy plane. I'm not sure exactly off of the top of my head where it would be, but it will be a function as far as we can tell here. So we might say that x equals f minus 1 of y. Now this little minus 1 up here means inverse. So x equals the inverse function of y. So if we take the inverse f minus 1 of y, we get x. Now the reader was confused because I chose to use y as the variable in my answer and in my explanation. I talked about the inverse is therefore f minus 1 of y equals such and so and such and so. Well, in this particular case, I use y as the variable and not x because we have an xy plane like this. And if we swap the axes and swap the function, we get x as a function of y. And that function, f minus 1, is the inverse of f. Now, that said, once we know this, and it's derived there, and it's a particular example, once we know this, we can say that the inverse f minus 1 can apply to just about any variable we may want. We can say that it applies to a variable called x, but that's going to introduce confusion because x is already spoken for here, and that's why I used y instead. But we could just as well use z. Well, We could just as well have our eraser go there and use a blank too. F minus 1 of z equals such and so in terms of z. F to the minus 1 of q, or whatever else we might want. But I use y in this particular example because we are simply swapping the roles of the variables. Y now acts in the role that x played before in the inverse. So it's natural to talk about the inverse of the variable y. And that's why I did that. I hope that clears that up for this reader. It's not really a mistake in the book, but it can cause confusion, and unfortunately, the confusion that it has caused here is precisely the kind of confusion that I was hoping to avoid by using this notation in the first place. I think there's something zen about that entire occurrence. The harder you try to accomplish something, the less likely it is that you will accomplish it, or something to that effect. But in any case, I failed to accomplish that for this reader, and I'm sorry about that. Stan Gibilisco signing off. Until next time, so long.